In this video, we'll be covering the basics of volumes by attachment. The idea of this particular concept is that we're going to go ahead and still have some kind of function f of x and g of x, and this is going to be systematically built such that we again have some kind of function on top and on bottom. In most cases, you'd go ahead and, again, to find the area of this object, you'd take the top function minus the bottom function. What we're generally going to do instead, however, is we're going to attach some kind of object to this region. In other words, we're going to go ahead and add a third dimension of space to this object. Now, in some cases, we might attach a rectangle. Sometimes we might attach a triangle, a half circle. In the first case, we end up attaching the squares all across this. Now, that makes this object very unique and very special because, again, as it gets closer and closer to this pinched location, those squares are going to get smaller and smaller. And then as we get to the, again, longer regions here, it's going to get larger squares. So the concept here is how am I supposed to find the volume of a three-dimensional object such that I have a function minus a function bounding vertically, and then that I'm attaching vertical squares to? Well, the idea of finding a volume is a simple concept of integrating from one value to another, but instead of just integrating over a function f of x minus g of x, we're going to actually integrate over the area of a specific type of object in respect to x. So in this particular case, if we're working with squares, the area formula will be whatever the function is that we're playing with, and I'm going to go ahead and use s. Let's just say the length here is s. Well, it's going to be s squared, because that is the area of a square. Now, if we're looking at a rectangle, well, that rectangle must be very specifically defined, so it's going to be, again, length times width, where hopefully one of those values will be s. Again, one of those values will be that length right there, or that length right there, or that length right there. And then my w will hopefully be some form of s. Okay, that way I can go ahead and utilize that appropriate formula. You then may have, say, a half circle. Recall that a half circle is nothing more than pi r squared, where my r, again, if I'm attaching half circles to this region, you're going to have some kind of awkward space, and I'll have, there's my diameter, and there's the half circle attached. There's the half circle attached. There's the half circle attached. In this case, that distance right there is the diameter, so 1/2 of that is the radius. Okay, so if this whole length here is d, then my r value will be equal to 1/2 of d. But I'm going to go ahead and continually use this little notion here as the distance of vertical. So instead of calling this d, I'm going to call this s. So that means that my radius in this formula is going to be 1/2 s, such that s is the distance between the top function and the bottom function. So that means I'm going to have pi r squared, where r is 1/2 s. Okay. Now keep in mind, what we're trying to do here is developing specific formulas for all different geometric attachments. We might have some isosceles triangles as well as equilateral triangles. The equilateral triangles are by far the most difficult. The isosceles end up being relatively nice, especially if we denote that the fact that the isosceles triangle is going to be attached by its right angle and one of the legs. So again, we have that right angle coming out, and there's that right angle again. Then we have this one here, and that's coming out, and there's your right angle there as well. So the area of this is going to be, well, since that length is s, and this is supposed to be an isosceles triangle, the area of any triangle is 1/2 base times height. Well, the base and the height are both going to end up being the same thing. Because again, there's the length coming down, that's s again, generally going to be referred to as f minus g. And then this height here is also going to end up being s because of the fact that this is an isosceles triangle. So the idea, one more time, is that we are going to simply go ahead and evaluate the volume of an object by evaluating the area of a function in respect to x by either using squares, rectangles, half circles, isosceles triangles, or again, we might have some equilateral triangles that we'll look at in another video.